Hello, my name is Changyo from the University of Tokyo. This was supposed to be my first KAI participation, so I'm so sorry that the event is cancelled due to COVID-19. I'm staying home safe, and I hope everyone's safe. This work, PneuModule, is a part of my PhD project, and it's done by my co-authors, Takahashi, Yuchi, Yahagi, and Takeshi Naemura. First, I want to explain the motivation and the overview of the project. It builds upon the vision presented by Nicholas Villa that user interfaces have to be malleable, which means that their forms and layouts have to be adaptable to the demand from users. Their prototype consists of a surface that allows physical controls can be dynamically placed, and they can be instantly recognized owing to the embedded microcontrollers and wired communication channels. This kind of spatial rearrangement of physical controls can be found on tangible user interfaces. Tangible interfaces inherently have features to recognize the position of the tangibles on the interactive surfaces. We can interact with the system by spatially arranging the tangibles, but it is often difficult to implement physical input capabilities to the tangible objects. Based on the aforementioned motivation, we propose PneuModule. PneuModule is a modular physical interface platform that works on pressure-sensitive touch surfaces. The layout of the physical controls can be instantly reconfigured owing to the inflatable pin arrays on the bottom of the modules, which can be actuated by passive pneumatic mechanisms. Owing to this configuration, the system can support both rigid and deformable user inputs. I'll then explain the related work. In the field of HCI, there have been a body of research that aims to make instantly reconfigurable physical interfaces. It can be accomplished by using electronics or magnetometers or RFIDs. These kinds of physical controls do not require complex wiring. Users can explore and adapt the interface layout. Using passive tangibles on touch surfaces offer both the spatial reconfigurability and the interactivity. Ohmic touch and flexibles use 3D printed conductive tangibles that accept user inputs. Geckos presented tangible interaction capabilities on pressure-sensitive touch surfaces. On our previous work for STEMs, we presented a physical interface prototyping tool using pressure-sensitive surfaces and 3D printed tangibles. On the view of deformable user inputs, there have been plenty of works that realize pneumatic pressure to accept user inputs. PneuModule extends interaction capabilities upon this work. Next, I will talk about the implementation of the PneuModule. We came up with the following design requirements. First, we needed mechanisms to transmit user input to the touch surface. Second, we needed modular design to recognize the interface layout. Third, we have to track the spatial position of the tangibles on the surface. So we came up with the structure shown on the left. Our system consists of two kinds of modules, our main module, which can be tracked on touch surfaces, and extension modules, which have physical input capabilities. The extension modules can be connected to the main module with airtight connectors and can forward user inputs to the inflatable pins through internal air pipes in the main module. The actuated pins touch the pressure-sensitive touch surface, thus enabling the user input can be transferred to the system. The figure on the right shows the implementation of the main module. It is assembled from rigid parts and main body and bottom lid, and the inflation layer is sandwiched between them, and there are 4 magnets to prevent the module from floating off the surface due to inflated pins. Let me show you how the pin inflates from the video on the left. As the user input is applied, the internal pressure of the air chamber increases and actuates the pin on the bottom. This kind of input forwarding can be implemented by other mechanisms, such as magnetic or mechanical ways, but we decided to implement it in pneumatic manner, since pneumatics can transmit the force continuously and can be implemented with less complexity. Next, to recognize the layout of the modules, we arrange the inflatable pins in a 2D array. We arrange 45 pins, which can be divided into 5 regions, and each region represents the state of the inputs coming from the corresponding side. The 9 pins in each region can be used either for representing the ID of the connecting module or forwarding the applied user input. We can see from the pressure image that it can be easily break out into different regions, and with a simple computer vision algorithm, the intensity of the blocks can be extracted. As the position of the pins are predetermined, the system can recognize the connected modules from the pressure image. And to track the main module, we place the permanent magnets in a rotationally asymmetric way, so it enables the system to track the position and orientation of the module. We have 2 different options for the pin actuation. One is actuation plug, and the other one is through-hole plug. When an extension module is connected to the main module, the actuation plug actuates the pin in the corresponding position, and the through-hole plug connects the air chamber of the extension module to that of the main module, thus forwarding the user input. Next, we explored the material and geometry options for fabricating the inflatable layers. We compared 2 silicons which have different stiffness properties. One is popular Ecoflex 030 with shear hardness 030, and the other is HTV 2000 with shear hardness 18A. We made a prototype with Ecoflex, and since the material was too soft, we encountered the following problems. First, the pins over-inflated even with small increase in internal pressure, so interfered with adjacent pins, making the system difficult to distinguish them. Second, when we slid the module on the surface, the pins caused positional misalignment to each other. Therefore, we chose to use slightly stiffer silicon HTV 2000 to restrict the amount of inflation. After that, we explored various options for the geometry of pins. There are mainly 2 factors that affect the inflation of the pins: thickness and diameter. With the shown design parameters, we fabricated and measured the inflation of the pin in 2 ways. First, we visually inspected the height of the pins, and next we measured the transmitted force using the touchpad. We used commercially available pressure-sensitive touchpad, SensorMorph. Among the design parameters, we found that the pin design with 5 mm diameter and 0.4 thickness shows the most considerable inflation characteristic, so we determined to adopt the parameters. Next, we designed the geometry of connector sockets and internal air pipes. The dimension of the sockets are determined by the plunger we used. We decided the geometry of the internal air pipe by considering the shown equation. When the socket is fully compressed, it resulted internal pressure of 3.9 to 5.3 atm, which is suitable for actuating the pins as shown in the former slide. To fabricate the modules, we used the SLA printer for the rigid parts, since it is difficult to obtain airtightness from commercial FDM printers. The inflation layer is cast by silicon and glued to the rigid body. Then the magnets on bottom lid are assembled. For fabricating extension modules, we printed rigid bases for connecting them to the main module. Syringe plungers are used as plugs for achieving the airtight connection. For user input, the air compression mechanism can be varied to offer different input modalities. For example, these rigid input modules have internal cylinders for air compression. For the press module, it is achieved by a linear motion. For the rotating module, we translated the angular motion to the linear motion by using screw thread. We also implemented extension modules that accept deformable user inputs such as squeeze, twist, and bend. To fabricate the deformable input, we cast silicon into 3D printed water-soluble mold and dissolve them in the mortar to make the internal air chamber. Then we connected the deformable part to the base of the module with a zip tie for airtight connection. We also fabricated an extension module that has no input functions but can alter the ID representation of the connected input module through it. It has the through-hole plugs except for one plug. This plug actuates a ID pin to make the change of the ID representation. Let me show you the operation of the modules. They are instantly recognized when connected, and we can see that user inputs are forwarded to the touch surface. And for a multi-dimensional input, we can assign multiple pins to distinguish them. And with the stack module, we can change the ID representation of the connected module. Finally, I'd like to show the application examples of the proposed system. We implemented a shooting game that the users can change weapons by swapping the physical modules. Each module corresponds to a specific weapon, and the user can customize the spaceship for different situations. For example, for this boss alien, user can equip a charge shot for to give effective damage. And new modules can be a tangible representation for virtual characters. Users can design the interaction in situ by swapping the input modules. In the video, the user swapped the stretching arm to the bending arm. Next, we made an adaptive music controller that tangible replication of the musical components. This clean guitar tone turns into distorted sound by inserting the distortion module through it, and additional controls can be added to manipulate the sound, like this volume knob. Finally, I will discuss the limitations and future work. First one is scalability of the system. As you can see, the size of the main module is pretty bulky compared to other modular blocks such as Lego. The scalability is limited by both the resolution of the touch surface and the inflation characteristic of the pins. To realize this system in a more smaller scale, we need a way to fit the resolution into the scale we aim for. And second, the surface friction increases with the number of actuated pins. This is because the silicon has acquired surface friction. In the demonstration, we mitigated the friction by using a dry lubricant, but we hope there is a better solution for this. And the final one is the fabrication process. We use different fabrication methods for rigid and soft parts, but with sophisticated multi-material 3D printing techniques that could be done in a single pass to reduce the cumbersome manual assembly. Okay, let me summarize my talk. We presented modular physical interface platform using pneumatically actuated inflatable pin arrays and pressure-sensitive touch surfaces. We derived a market design for tracking and recognizing the configuration of the modules. We explored various inflatable pin designs for force transmission and showed diverse application examples of the proposed system. If you have any questions, feel free to contact me via email or Twitter. Thank you.